Okay, there we go.
Just for clarification, there's homework due tonight and presentations are next Monday, right?
Yep, correct. So in last lecture, we talked about the some of the properties in the metal additive printing. For example, we talk about the vaporization for the alloy elements used in the metal additive. So for different elements, because there are vacuum environment in the, especially in the electron beam melting process, and these elements could have could be vaporized due to the vacuum and the high temperature. So that is essential to look at what temperature and with the given vacuum, these elements could be vaporized, such that you will determine, okay, is this material available for this process or not? If I could use this material for the EBM process or not. So this is very essential. And basically what we could do is looking at this vapor pressure curve of the elements. So the vertical axis gives you the pressures in torr. And also you can convert it to this newtons per square meter. Usually torr is good enough. Sorry. And here gives you the temperature. Also, you can see there are plenty of curves. So each of the curve represents the it represents for a specific element if there will be a vaporization happens or not. So what you could do is, for example, given a pressure, also given a temperature, you just find out what is the intersection. For example, let me look at the specific example here. Okay, 100 degrees C and also 10 power by -3. Okay, let's look at this specific case. Basically, you just draw a straight curve, and also 100 C. Oh, I think my drawing is really bad. Let me clean it up and redraw this part. It's hard to draw a straight line by using just the mouse. That's not good. All right. And like 100. No, it's not. Let me try to make it really straight. All right, I mean, something like this. So by looking at this, basically the intersection point is here. On the other hand, if we look at the aluminum, for aluminum, see, this is the curve for the aluminum, and it's off. It's not on the curve, and actually it's on the on this side of the curve. That means at this point there will not a vaporization happens for the aluminum elements. I mean, basically you can do the same thing for other elements when given a specific pressure for the vacuum as well as the temperature, such that you could understand, you could have the understanding if that element will have the vaporization happens for under this condition or not. So this is the vaporization, vapor pressure curve for the elements. Also, there's a shrinkage compensation need to be done when you do the design, because when the part cools down, it will shrink. In that case, if you design your part to be at the scale you want the final part to be, that will be an issue that it will shrink to a smaller size. So in that sense, you want to scale up what you designed before you put it before you utilize the EVM printer to print the part. And there's some heuristic. Basically, it's material depending, right? For different material, that will be different shrinkage factor. And for the compensation, the factor will be also different. So if you're talking about the this H13 tool steel, the shrinkage factor is 1.4%. That means you want to scale up by 1.4% for the size of your design when you come up with the design. And for this titanium alloy, then the shrinkage, the shrinkage compensation factor is 1.0086%. And that's for X axis. For Y and Z, there are different, here is another percentage, right? There are different numbers. For X and Y, it is this one, and for Z, it is this one. So again, because this process is layer by layer, that gives you the different ratio for the shrinkage in X, Y direction as well as Z. So that's why there are different numbers. So that is what you want to keep in mind when you have a design task for EBM process. Also, the cooling of the printing material, specifically steel, will be critical, because the cooling speed will lead to different material property. Usually a slow cooling lead to a very soft parts. But on the other hand, a fast cooling will cause the part to be brittle and hard. So that will change the material property. The reason is the rate at which the temperature drops will affect the crystal structure of the material, and that change the material property and mechanical property of the parts. Usually, a very small cooling will lead to softer, more ductile material property because the grain size is larger. There are more larger grain formed during a very slow cooling. On the other hand, a rapid cooling typically lead to a harder, stronger, but usually brittle material property for the parts. So that is what you want to keep in mind. Again, depending on the applications, what's the material property, mechanical property you would like to have for the printed part then you can decide how you cool down the part, whether it's a slow cooling or a rapid cooling, right? For the titanium, that's a little different. Since titanium is easily oxidized, so that means you don't want to cool down titanium in an oxygen environment. In that sense, basically you want to keep it in the chamber with no oxygen there. It is dangerous if you allow the air into the chamber when titanium is still high. That could be a fire, right? That is what you definitely want to prevent. Especially their powder material, which is really easy to explode. That, I mean, for the sake of safety, it is prohibited to introduce air to the build chamber when the temperature is still high. So that's the critical thing you want to keep in mind. And usually the cooling happens with the helium gases. So the helium gas will not have chemical reaction with titanium and powders and the part. So that will make sure there won't be the oxidization happens. Usually it takes 10 to 12 hours if you do not have the helium gas filled. But with the helium gas filled, the cooling time could be reduced to 2 to 3 hours. So that will speed up this cooling process dramatically. So the post-processing is also critical as well for the EBM printing. And first thing first is to remove those centered material. So what you could do is a vacuum process to remove those loose powder. And again, so that the safety is still quite critical, because you are dealing with powders and there's a risk of explosion. And when you use the vacuum, so definitely you want to make sure the vacuum used is a explosion-proofed motor. There won't be electric sparkles there during the usage of the vacuum. And again, the metal wires is to clean the conformal cooling channels. That is another post-processing during for the EBM process. So for the both EBM and also the selective laser melting, the post-processing takes a significant amount of time. So that's why that makes the whole process complex. And that's why it's not widely used. But for those applications such as aerospace and like biomedical, it's worthwhile to utilize such processes to create high quality complex geometry and also lightweight products. So it can justify the difficulty as well as the cost. And that's the major applications for the EBM and also the selective laser melting. There are some restrictions for the EBM, especially for the designs. Basically, you want to leave approximately 1 millimeter of additional material on the critical surfaces, because you always need to machine your part to have a better surface finish. That's why a additional material should be there for the machining. You want always to create a bigger part than it is, such that the machining, after machining, you could have the right geometry of the part. So I think there are also some other considerations if you want to install the EBM machine in your facility, because this EBM process utilizes the electron beam, and it is controlled by the magnetic field. So you don't want to have other magnetic field to be around, such that could interrupt the, that could affect the magnetic field in the machine. So such a low frequency magnetic field, such as 50 to 60 hertz power cable, is prohibited to be placed near the EBM guns. Also, you want to avoid moving large steel item close to the machine during a building. Again, that is because the working principle of EBM. You don't want to have metal, especially steel parts, close to the machine when there are electron beams in the during the building process. Here show you some surface finish of the part, and also some macro scope pictures taken. As you can see here, shows you the surface of the part, and also apparently the direct metal laser DMSL, DMLS shows a smaller feature size, and the EBM gives a relatively larger feature size. So for the accuracy, the DMSL or DMLS have a 0.27 millimeter thickness for the walls, and the EBM with the 0.4 lenses will give you a 0.5 millimeter thickness for the minimal walls. Accuracy, apparently, this gives DMLS gives higher accuracy. On the other hand, the EBM is relatively inaccurate compared to the DMLS. The maximum machine size. So basically, DMLS have a 0.4 meter part, and the EBM only has 0.2 meter size for the maximum part size. So as you can see here, it seems DMLS can produce a larger part plus a higher accuracy and parts with smaller feature size. But the EBM has the advantage of the building speed. It's faster than the DMLS, and that's why this EBM is still in use in many applications. If these consideration of the smaller feature size, accuracy, and the maximum part size is not critical, right? So here show you some of the materials you could utilize for these processes, and also for the lasers, right? So a critical thing for these process are the power and the velocities. So how big the grain size is associated with the melting pool width. So as you can see here, these figures show you how it will affect I mean, especially for these ones, it shows you how the melting pool dips will look like if there are different power and velocity specified. So that will give you some idea about how this would change. So as you can see here, the velocity is positively proportional to the power. As you can see here, basically it's more like a linear relationship. So in that case, you can predict how the final build will look like if you have a specific velocity. I mean the scanning velocity as well as the build power, right? So if we take a close look of those build part by the EBM process, if the power is increased, there will be deeper and more pronounced melting pool generated. I mean, that's intuitive, right? If the power is bigger, then it's obvious the powder will be melt more, and there will be more the melting pool will be larger, right? That makes sense. If the velocity is lower, I mean, all the rest keep the same, but the velocity of the electron beam scans is lower. That means at a specific region, there will be more electron beam hit onto the powder, and that would also increase the melting of the powder. So a wider melting pool are generated with a lower velocity. And also there will be a grain refinement in the melting pool if the powder is larger and the velocity is lower, right? But on the other hand, there will be more energy consumed for with a larger power and a lower velocity for the process. And so here show you some of the metal powders characteristics. Basically, it is critical to look at the powder. It is desired to have a more unified distributed powder size, such that the built part will have more consist mechanical and material property, and the grain size will be also more consist. So, I mean, I don't want to go too much on this along this direction. There are quite a bit paper discussing the effect of the powder size versus the final build part, and in short, the conclusion is pretty critical of the powder's size and quality. So another consideration is the ratio of the width and the height of the powder. So if we consider the powder to be a ellipse solid, there will be a ratio between the longer axis and the shorter axis, and that ratio will affect the volume fraction. Basically, if the ratio is 1, that means it is a spherical powder. But in general, it is not the case. Usually, there will be a different there will be a different ratio, and usually it is larger than 1, and that will give you the different volume fractions. So the pro and volume, I mean the pores and voids are the defects during the process, and these should be avoided. And that will, I mean, if this happens, there will be a stress concentration points, which could increase the possibility of cracking at such a point. So always the pores and the voids are definitely are the critical points people want to look at to improve the quality of the prints for the metal printing process. So here gives you a little comparison of the two process for the laser-based and the electron beam-based. So for both of the two process, they are very expensive as well, but they have different different components which requires high cost. For the powder-based one, the laser, high power laser is very expensive, and you have to replace it every few years. And for electron beams, the filament which are source to generate electron beam and also requires a replacement. Approximately every 100 hours to have a new filament. And for each of the replacement, it costs 100 also, right? And the materials, basically it depends on the electrical conductivity and optical reflectivities. And these are the consideration if you choose the materials. They are highly energy intensive process. For the laser energy, it is roughly only 14% in terms of efficiency. On the other hand, the electron beams are about 90% energy efficient. There will be some safety concerns for both of the two processes. For example, the UV light would be generated during the process, and the X-rays, UV light would be generated for the laser-based approach, and the X-rays will be generated for the electron beam based approaches. Both of them are hazard to human operators, and there need to be the protections when people operate these processes. And well, on the other hand, there are some consideration when you want to choose either the laser-based or the electron beams based processes, and that's still open because both the two processes are still under development, and there are quite a bit money invested in both the two processes. Because, as I mentioned, because in some of the applications, it is critical, and these processes are the good candidates for those applications. So you can think of some of the pros and cons for both of our processes, but still, for the consumer level products, it is really hard to utilize the two process due to its high cost and also the complexity for the whole preparation and the post-processing and so on, right? So that's pretty much what I want to introduce for the metal printings. Also, there are some research directions. For example, when speaking of the metal parts, there's always a comparison between the metal additive parts versus casting and forging, right? Which one's better in terms of the mechanical and material properties, as well as the cost and the time cost, and so on and so forth, right? Especially also for the part size, you cannot build too large size for the metal additive right now, but for the casting and other processes, other metal processes, there's no such a tight limit in terms of size, and how to avoid those defects for the parts during the process. These are all open questions so far, and under research, as I mentioned. And so here shows some additional research questions, such as the qualification, and a difficulty for the part produced by the additive manufacturing is it's the inconsistency of the parts. It's hard to have a unified mechanical properties for amount, even with the same, even with the parts produced by the same machine using the same material. The mechanical property and the material property could be different. I mean, that's the biggest challenge for this process fundamentally, right? That will make the part qualification and standardization to be really difficult, and that's a big concern here. Also, the powder, because the powder are the primary materials utilized. If the recycling of the powder cannot be operated easily and effectively, that will be a big waste, because the powder is very expensive and process the powder is very expensive and complex. So the recycling of the powder is critical as well. and oxygens, right? You can see how, I mean, for both the process, how to avoid the oxidization is really troublesome, and there are plenty of efforts devoted to avoid the oxidization and how to realize the oxygen free during the printing process, especially for the EBM with titanium, right? That will be very critical questions to be solved in the ongoing and the future research directions. Okay, I think that's all for the metal additive printing utilize the powder-based process. And let's have a break and let's go back at 11 o'clock, all right? Okay, let's move on. So let's talk about some of the mechanical elements of 3D printers. So far we have talked about quite a bit additive manufacturing processes, and you will see there are quite a bit elements are in common because of this layer by layer process. So let's have a more detailed look at those elements. Basically, the objective is to get more familiar with those mechanical hardwares utilized in most of the 3D printers. And also you could do some basic calculation to control the motion of those 3D systems, specifically the distance and the speed, because that will that are the critical parts for the 3D printing for one 3D printing process. And let's look at them one by one. First thing is the microcontrollers. That is considered as the brain of a 3D printer, and it includes the process, the central processor, the motor driver, some of the power management, and also the heat and end stop sensors. As you can see here, show you a typical microcontroller systems. As you can see here, there are motors, there are control units for the motors for different extruders. Also, there are motors to enable the motion in both X and Y direction. And there are two motors here shown for the motion in the Z axis and so on. So for such kind of microcontroller, there are plenty open source firmwares associated, and like the ones shown here. And to me, this one, Rambo, is pretty popular. I didn't see others personally, but I do work with Rambo hardware packages, firmware packages previously. And that it is widely used for different 3D printing, 3D printers. So basically they are based on the same hardware and share many common features. And that make the programming with those microcontroller much easier. And you could look into some of these well-known ones and see what they did. So as I mentioned, the sensor system are one of the key components for the microcontroller. Basically, that will detect when the item moving along an axis has reached one or the other end of the travel, because without the sensor, there's no way for the printer knows where your where this nozzle is. So it has to go through this in the very beginning. It has to go through this so-called home operation. Basically, you will see the printer will move in the X, Y, and Z, and it will reach the end along each of the axes. And after that, the whole system is ready to perform a new task. And that's how this sensor would work. And there are different types of sensors. We have the mechanical ones, optical ones, and magnetic ones. If you look at those figures, it gives you some idea about how this could be, right? So, but no matter which type of sensor utilized, basically the sensor will give two states. One is NO, another one is NC, and NO means normally open, and NC means normally closed, and that will be achieved by an on and off of the sensor signal during this the initialization of the printer's printing system. To detect the temperature, there are also other sensors like the thermistors, the RTDs, or thermocouples. These are all the thermal sensors to detect temperatures, especially when the printing nozzle hot end is heated up. It is critical to know what's the temperature the thermal or the hot end is at a specific moment. So these will be utilized in such a process. And another component is the PID algorithm. So the PID is the proportional integral derivative control algorithms, and that is used to ramp up the temperature on a printing bed, the printer head, and other heated elements as quick as possible without a overshooting. The overshooting is prevented because there are specific, very restrict requirement for the temperature during the process. You don't want to have a temperature over it's supposed to be, right? So this is the PID algorithm utilized here, and that's by the way, the PID is a sorry, is a very widely used algorithms in many control systems. But here, this is specifically for the temperature control. All right. And another point here is the positioning resolution. So in a motion system, basically the positioning resolution gives you the idea that what is the smallest distance you could ask the system to move in any direction along any axis. And that is how this positioning resolution is determined. Actually, that there are multiple effects. I mean, there are multiple aspects to affect the positioning resolution. Basically, how you select the motor, there are different motors, and the pulleys, right? Pulleys you choose, there are different parameters, diameters, I mean. So that is usually for the X, Y direction. In the Z direction, there are screws has different pitches, and the pitch will determine how many, what is the distance travel along this direction per revolving of the screw, right? That these are the another aspects to affect the positioning resolution. And these will be introduced in the next few slides. Also for the control system, there will be a open loop control and a closed loop control. Open loop control is like there's only one direction. Basically, once you once the command is sent, there's no way back. And closed loop control is like it will have a sensor feedback to affect the command sent to the microcontroller and so on. So that will make the process more robust with the closed loop control. And but usually many 3D printer, especially the low cost one, there's no closed loop control. It's just a one shot operation, right? So the motor are critical for the 3D system's motion system. And there are different types of motors: DC motor, servo motor, and step motor, right? So the DC motor is the simplest one. It has only one state, two states. One is on and another is off, and that's it. You don't have much control on the DC motor, but that's not the case for us, right? We definitely want to have a relatively precise control on the motion, on the revolving of the motor. So that's why we usually look at the servo motor and the step motor. So the servo motor has encoder there, and that will control its motion. On the other hand, the step motor takes the synchronized pulse signals. Basically, each of the step signal sent will cause a motion of the motor. So in the 3D printing systems, the most used one is the stepper motor. By the way, if we talk about the cost, usually the servo motor costs the most because it's more complex, and the stepper motor is the second expensive one, and the DC motor is the cheapest one usually. In general, I mean, depending on, basically, you can tell it really depends on the complexity of the motors, right? And as I mentioned, the stepper motor receives command to rotate their axes in the discrete steps signals, right? So each step of motion will, by the motor, actually give you the smallest rotation increment could be achieved by the motor. So if you look at this illustration figure, see, basically at each step, each of the one coil, the wires or a pair of wires will be energized, and that will drive the motor. The motor rotate a certain degrees. As you can see here, it rotates 3.6 degrees per step. So that is how you could have a relatively precise control on it. So when each of the step signals sent to the motor, this will rotate by 3.6 degrees. That's how it works, right? So
excuse me, Professor.
Yeah.
I'm sorry to interrupt, but could you please assign captioning to me?
Oh, what was that?
Could you please assign captioning to me?
Yeah, just one second.
No problem.
Yeah.
No, thank you.
Yep. Just 1 second. I think I need to stop the sharing such that I can see your. Just 1 second. Okay, I think now I got it. There we go. Okay. So there's a special type of operation which is called the microstepping. So that is, since we have our smallest I mean, we have we have this angle, which is the rotated angle per step determined. Instead of just utilize that to make the rotation smoother and to reduce the noise of the motor, there's a way to further reduce the steps, which is called the macro stepping. Basically, that will make the motor moves with a smaller step than what we determined previously. I don't know whether this has a caption. If not, I can give you an explanation.
The stepping motor can be controlled by a micro.
Basically, this is I think there's no caption. I can introduce this. So basically, as you can see here, if you see the motion of the motor, each of the between the two. Let me pause it here. Okay, so basically, between each of these two lines, that is a step, how much the motor will rotate per step. But as you can see here, actually this motor moves in a smaller steps. See, there are smaller steps in their motion. So basically that is what the macro stepping does. So that basically there will be a smaller motion realized with the macro steps. As you can see here, this black lines shows, well, that's the macro steps. Otherwise, it will move just from here to here for each of the steps. So that's the macro stepping. Basically, that is for reducing the noise and the vibration of the motor during its motion, right? And there could be some little conversion here. So the step per, basically, you could have the two information given. One is steps per revolution and the degrees per step. So if a motor has 200 steps, if a motor has a 200 step per revolution, then how many degrees will the motor turn per steps, right? So let's look at it. So if you have 200 steps, let me use the pen to write. That will, just 1 second, let me erase this. Okay, there we go. Okay, well, we have 200 steps per revolve, right? And we want to find out what will be the degrees the motor turn per step, right? There are 200 steps per revolve. For one revolve, for one revolution, there will be basically there will be 360 degrees here, that right? So in that sense, for 200 steps, the whole motor revolved 360. Then what will be the degree per step? What you want to do is you have let's do this calculation here. So what you want to know is degree per step, right? And you also know, okay, for one revolve, that's 360 degrees per revolve, right? And in each revolve, one revolve, there will be 200 steps. That's given, right? That is what given. Then 360 degree over 200 step, and that gives you the degrees per step, which is let me think, that's 1.8 degrees per step. So that's how you have this information ready. So basically you need to understand what does it mean? What is the steps per revolution and what is the degrees per step? So does it make sense to you for this calculation?
Yep.
Okay, good. So and also for the micro stepping, I skipped the details, but this micro stepping actually is achieved by a lower current or lower power. That is in between of the two steps. There are lower current given to the motor, and that will make the motor revolve a much smaller angle. That's how this macro stepping achieved. For example, you could have a 1/20 macro stepping. That means you could rotate the motor 1/20 of a step when this macro stepping is used. In this case, basically for this amount, 1.8 degrees, that's the degree motor revolves per step, right? But actually you could, if you have such amount of macro stepping, that means you could revolve 1/22 of 1.8 for a micro stepping, right? That's really small. But on the other hand, you don't necessarily rely on the macro stepping resolution because you are using a lower power or lower current to realize this macro stepping, and there's no guarantee on the accuracy for the macro stepping. So, well, probably you will have something close to 1.8 times 1/32 as the macro stepping, but you don't want to rely on it because it's there's no guaranteed precision on such a macro stepping. So if you talk about the motor resolution or accuracy, you always want to talk about this instead of the macro stepping. All right, because you have no control on it, on the macro stepping. All right, so that's the motor degree per step calculation. Another thing is the size of the motor. So actually there are standards for the size of motor defined by the National Electrical Manufacturers Association. Here shows a family of motors with a different size, with all different size. So you can tell the size by looking at its name. So the NEMA are the initials of the four words here, and this number actually that is the actual size of the mount face, actually the width of a mounting face times 10. And that's this number. For example, if you are looking at a motor NEMA 23, that means a mounting face width is 2.3 inch. 23/10, and the unit is inch, right? So now you know, okay, probably you want this big, at least this big, this big for the mounting face of your motor. Otherwise, you cannot use it. There's no enough room for such a motor, right? So basically, it gives you the information of the size of the motor, right? Also, the encoders, there are rotary encoders showing here for changing the for controlling the motor. And there are multiple ways: mechanical ones, optical ones, magnetic ones, and capacitive ones. And here it gives you a optical ones. So basically, at each of the as you can see here, basically it utilizes these three sectors, and it could be in a dark gray color or a bright color, and basically it's the and that each of the color will give you a different state. For example, a bright means 1 and gray means 0. So by combining the three, you will have all 8 different combinations, right? So it's just this gives you the bit. If you ever learn any programming, you know, a bit will give you 2 states, either 1 or 0, and one that is what 1 bit could give you, right? But if you have 3 bits, just like the case here, these 3 sectors, and if you have 3 bits, it gives you 8 different combinations. So by doing so, that will give you these informations and give you the different angles. So I don't want to go to the details of this, but just to give you some idea that this is still utilized a bit to represent the information, and which is exact the same strategy utilized in the in your computer or your cell phone, right? And then we look at the motion stages. We have the X, Y motion as well as the Z motions. And they are realized, usually they are realized in different principles. Let's look at the details. I think here is a video, and let me show you. See, you can see the XY motion of the nozzle, and after a layer is completed, there will be a lifting along the Z axis as well. And there are different components to enable the motion in X, Y, and Z. Here, basically, these timing belts and also pulleys, motors, are utilized for the XY motion, and along the Z directions, there are screws, and so on and so forth. So let's look at the details. Basically, the belt and pulley are driven by the step motors, and the positioning resolution is determined by the stepper motor's resolution and the diameter of the pulleys. So basically, you can see that here gives you the stage, XY stage, a detailed look of this XY stage. And as you can see here, these 2 rails are in parallel, and that will make sure the X and the Y are parallel, because let me draw a little illustration here. So this is X and this is Y. If these are not parallel, then the orthogonal of the 2 direction cannot be guaranteed, and that will make the XY motion inaccurate. So as you can see here, these are the bronze or nylon bushings. So these are the lubricating bronze, which will prevent the high frequency, which will prevent the high friction of the motion in the XY direction. Also, you want to always polish this reel made of steel, because if there are some dirt or other or stain on this steel, there will be a large friction produced when this move along the reel. When this part, basically this is the motion part, and it will move along the reel, and this is already the self-lubricating part, and this you want to prevent if there are any dirt or stain produced there, and that's the requirement to make sure this motion to be successful. There are little calculation here. As you can see, basically this pulley will be connected. Let me draw some illustration. Will be connected by the motor, right? This is the motor, and this is the pulley, and then this the printing platform or the motion part will move along this direction, right? That's how it works. Basically, it is the same for the X and the Y direction. So let's just look at one direction, and that's good enough to represent how it works. There are some information you could be given, that is the motor's revolution per minute. Actually, that could be controlled by you, right? You could give a different signal to the motor, and the motor will revolve. At the same time, it will drive the pulley rotate, right? And there could be some a discussion here. So in this case, we assume the pulley is directly connected with a motor. That means if motor revolve rotate 360 degree, then the pulley will also revolve 360. But that could be some gear system. For example, if the motor is not directly attached to the pulley, and instead it attached to a gear system, and then the gear attached to the pulley, and this is the pulley. And this is connected to the motor. Then you probably need to utilize the gear ratio. There's a gear ratio for the gear system. Gear ratio. For example, in this case, if I think I draw maybe this one's bigger and this one's smaller. Okay. For example, if this this gear rotate one turn and this one rotate 3, and then the pulley will rotate also 3 turns when the motor rotate 1 turn. So basically that is depending on how you connect the motor to the pulley, if there is gear system or not. That need to be considered. So if if there is a gear system, you need to use the ratio to come up with the revolution per minute for the pulley when given the revolution per minute of the motor. So does it make sense to you for here? Okay, I think it's straightforward. And when the pulley revolve, it will drive the belt to move linearly. And as you can see here, it will drive this black dot move along this axis linearly. All right. So for example, if you already know the pulley diameter and also the pulley is connected to the motor directly, then how you come up with the the distance of the black dot moves with one rotation of the motor. So as we know, if motor moves one turn, the pulley also rotate one turn, and that's the assumption if there's no other information given. If there are gear system given, that will be different. You have to do this conversion, right? As I mentioned previously. But let's assume the pulley is connected with the motor directly. So with one turn of the motor, this pulley will also move one turn, and that means this pulley travels one of its circumferences. So in that case, you just need to compute its circumferences. So that is pi times its diameter, which is d, right? And that will be the motion of this dot. And that gives you how much the dot will move if the pulley revolve one turn. In this case, also the motor revolve one turn. This gives you this number here. Does it make sense to you? Any question regarding here? Okay, good. So I think we have, okay. Yeah, we talk about this. And also we have, let's take more look at it. So for one rotation of the motor, and then if we want to figure out how many rotation will the pulley make if the motor is directly attached to the pulley. That is because you are assuming there's no gear system there. So if there's a one rotation of the motor, and if there's no gear system, if this was wording there, that means there's no gear system directly attached. That means no gear. That is, then that gives you the information, one rotation for motor, then that there's one rotation for the pulley as well. So that's how it works. On the other hand, if there are gears, you need to know the gear ratio, and that gear ratio is will give you this information. For example, if the gear ratio is 3:1, then you need to for this is connected to the motor, and this is connected to the pulley, and this revolves 3 turns, this revolve 1, that will, you need to over 3 with using the revolution of per minute of this motor, such that you will have the revolution per minute of the pulley, right? Also, there could be some other cases. It's 1/3 the gear system. Just 1 second, let me write it up. 1 to 3. That means this revolve 1 turn, this will revolve 3. In that case, you want to multiply the revolution of the motor by 3, and that will give you the revolution of the pulley per minute. So that is what you want to be aware of if there are some questions with gear system given, right? But otherwise, if there's a direct attachment of the pulley with the motor, then that will be the 1-to-1, right? So knowing these two, knowing the revolution of the motor, and also you know the you know what is the how many, what is the relationship between the rotation of the pulley and the motor, you could come up with the speed of the pulley spinning, right? So how to do that? For example, you have a motor turns at n revolution per minute, right? And you want to come up what is the pulley spinning, but in millimeter per second. Then what you could do is first do a conversion of minute to second, because finally you want to have the second instead of a minute as the unit. Then you could 1 minute actually is 60 seconds, right? And also you have come up with, for 1 revolution, this pulley travels pi dp millimeter. That's per one one revolution, right? That's what you just come up with here, right? That's how, for 1 revolution, how far the pulley spinning, and also how far this block dot moves, right? That's what you come up with. And multiply them together, you will have this pulley spinning speed. And you can see the second, the revolution cancel out, minute cancel out, and turns out you have millimeter per second. And that is n pi dp over 60 millimeter per second. That's how you come up with the pulley spinning linear speed in millimeter per second if you have a motor turning speed in a revolution per minute. I think I can clean it up because I have better written ones showing here, right? That's the equation you want to keep in mind. And also, if sometimes you have a desired velocity in millimeter per second, but you want to know what will be the revolution per minute of the motor, then how are you going to do? Basically, you want to revolve this, reverse this process, right? basically you've already know this, the left-hand side, and you want to come up with the n, then do the reversed calculation, and then you will have this motion turning in revolution per minute. But be aware of the units. That's critical. That will give you a trouble if you are not aware of it. All right. So I also listed it out here. If you want, you can do a verification yourself. But basically, that is the reverse process of this one. Okay. So if you want to move the black dot at a distance of x millimeter, then how many revolutions should you turn the motor? So basically, you've already have you've already have the dot move speed, which is pi dp millimeter per revolution, right? You've already know this speed in per revolution, and you know the distance is x millimeter. Then how many revolution of the motor is? Just simply use the distance over the millimeter per revolution. Then you will have the revolution number, revolution of the motor came up with. So that's also a calculation based on this equation, the dot movement in millimeter per revolution, right? So for the z-axis, it's a little different. Instead of using the pulley and belt system, it utilizes a cantilever platform. Basically, the critical part is this lat screws. And basically, there's a concept called pitch. So that is that gives you the idea how many distance it travels along this axis. If you revolve this screw for one turn, so this pitch will be the distance this travels if the screw have a one turn. So that gives you the idea, if you want to travel a certain distance, how many revolve this screw should be, right? By utilizing the pitch and also the distance travels. So let's look at some details. For example, you have a pitch P given here. And also, again, this screw is directly attached to a motor. That means if motor turn rotate one turn, the screw will also rotate one turn, right? Same thing. If their gear system, same thing, do this conversion using the gear ratio. But if it is directly attached to the motor, then one turn of the motor will have one turn of the screw. Okay, then the question is, how many motor rotations are needed to move the knot at a distance of x millimeter? So basically, you have pitch. Basically, pitch gives you how many millimeter this will travel if the screw is rotated by one turn. And in that case, x over this pitch will give you how many turns it requires to achieve this motion in this direction by x millimeter. So does it make sense to you here to come up with the turns, the rotations? Okay, good. So that could be some other questions in the opposite direction. Again, for example, there's a pitch given, right? And you also know the screw is attached to the motor directly. And now you don't want to know the turns, but you want to know the speed. So that is the revolution per minute. Also, there's a desired speed for the linear motion, V millimeter per minute. You want to come up with the motor speed in revolution per minute. So how you're gonna do is what you could, since they are all in minutes, this linear speed is V millimeter per minute, and this motor speed is revolution per minute. So you don't need to worry about the conversion of minute and second, right? So this is V millimeter per minute, and you want this over P millimeter. Actually, that is over the pitch of the screw. And by doing so, you will convert this linear speed, linear velocity to the rotation of the motor. So here, so you can see the similarity of the two process. This is, for this one, you know the distance, right? You know the distance you want to move, the linear distance you want to move, and the unknown is how many rotation it is necessary. Then use the distance over the pitch. Then you will have the rotation of the screw. Here, what you know is, you know the velocity along this, the linear velocity along this direction. And what you want to figure out is the motor speed, that is the revolution per minute of the motor. Again, over this pitch, you will come up with the revolution per minute. So same thing, both are, you need to over this pitch, and then you will have the result. So that's how you could do this conversion between the linear motion and also it's the revolution of the screw or the motor. And in the opposite way, if you know the revolution, either the distance, either the turns or the speed of the resolution, you can easily come up with the distance it travels along this direction, or the speed it travels in this direction, right? Does it make sense to you? Any question about this? Okay, good. So another part is the G code. So the G code is the code to control the motion of the printing head, and it will give you some X, Y directions, positions that will be where the printing head will travel to or from, right? Also, there will be speed of the printing head will in the motion. So this is how the G code will work for a 3D printer. So if you, during your lab session, the last step before you actually print the part is to export the G code, right? And then the printer will read through the G code and know what to do. So that's how this works. So I don't want to go to the details, but there are very nice website gives you a comprehensive explanation of the G code. Basically, these are all the commands, and for each of the commands, it represents a certain functions to guide the motion of the printing head, and you can look through and have some understanding of it. Okay, let's see a example questions. And basically it is the combination of what we learned so far, right? Let's say you have a lead screw with 60 with 16 thread per inch. By doing this, you could compute the pitch, right? Basically, if you look at this figure, see, the pitch is also the distance between the two threads, right? And you know, there are 16 threads per inch. Then you can easily compute what is the pitch. That is 1/16 inch per revolve. That means for each revolution of this screw, it travels 1/16 inch linearly, right? And then this screw is connected to a stepper motor, and this stepper motor have a 1.8 degree per step, 1.8 degrees per step. And now you want to move the knot a distance 1.5 inch, and the speed is 10 inch per minute. Then there could be a few questions for you, right? So first thing is how many steps this motor need to be turned for travel 1.5 inch. So you have the distance, and you know, for each of the, the pitch, that is one revolution. For one revolution, this knot, this thread, this screw will move along in this linear direction. Then what you could do is simply use 1.5, and 1.5 is divided by this pitch, and then you will come up with the revolution. Since they are all in inch, right? They're in the distance is represented by inches, and this pitch is also represented by inch per revolution. Then you can easily have the 24 revolution for traveling this much of the knot, right? Then this another question is, actually this is asking you the steps, not only the revolves, right? Not only one revolution. So this 24 actually is the revolution of this screw, because of this screw is directly connected to a step motor. That means if it requires the screw to rotate 24 revolution, that means this step motor also need to revolve rotate 24 revolution. So by knowing this, you can come up with the steps the motor will be turned, right? So you have 24 revolution, but you have to know for one revolution how many steps this motor will have. You also know per step it revolves 1.8 degrees, and for each of the revolution, it will be turned 360 degrees. Then you will come up with this. That is the steps for the motor in one revolution. And now you have 24 revolution. Then multiply this with 24, you will have this number, which is 4,800 steps for turning the motor in 24 revolutions. Okay, it's a little complicated. So any questions? Does it make sense to you? Any questions? I just want to make sure you understand it, because for the homework there will be similar questions. Okay, good. So that is the steps, right? Then the second question is what speed the motor should be turned, right? So what you could do is, well, we already know the motor the motor's rotation will be identical to the screws rotation, and we also know this pitch as well as the speed, the linear speed, as I mentioned here, right? You can always do this conversion by knowing the linear speed as well as the pitch. You can either know the linear speed and then come up with the rotation, or know the rotation and the pitch, come up with the linear speed. Now what you know here is you know the linear speed and also the pitch. You can easily come up with the revolution per minute, and that is what you have. All right. Any question for this? Okay, good. I think probably you want to practice more how to utilize these equations by go through some questions in the homework. I will release the last homework right after the end of the class, and still the deadline for the homework is next Monday, probably 10 p.m. and that will be the last homework. All right. So then we have some other machine configurations instead of the XY based ones. There are delta ones, there are polar based ones. Basically, you can see the video. There are some rotation axis instead of XY motion. I don't want to go to the detail of this. You can look at the video yourself. I think that's all for the mechanical elements of the 3D printing. And that's all for the lectures of this class. So I think we still have little time. Any questions? Okay, if there's no question, please please notice the please be aware of the last homework, and I will release the grade for homework 4 by tomorrow, 3 and 4 by tomorrow, and that's pretty much the end of the semester, and I really want you to focus on the project, as well as you need little time to review the whole class and work on the final exam. And also want to clarify, the exam 2 will be combined with the final exam. So there's no exam 2 separately, all right? Any other question regarding the course? Okay, if there's no more questions, so let's end the class, and thanks for your attention. And I look forward to your presentation next Monday.
Professor.
Yep.
Thank you. Have a good one.
Yep. Thank you. Bye, guys. Mhm.